This week, we will focus on looking for differences between two groups. Now, to do this, we are going to work through all of the steps of doing an independent samples t-test in JASP. What you learn today will help you with your weekly quiz assignment and the test that we do at the end of the 4-week block. So here is the setup and the steps that you need to know. We will begin with the research design. A researcher on the Business School Admissions Committee hypothesized that student applicants whose parents had achieved a higher level of education would, on average, score differently on the Scholastic Aptitude Test, the SAT. The researcher acquired a set of SAT math scores and then determined whether the applicant's parents were college graduates with a bachelor's degree or high school graduates who did not have a college degree. Conduct an independent samples t-test and answer the following questions about your findings. Well, I want to start with the actual research question. In this case, the research question is, do students whose parents have a college education score differently on the math SAT than students whose parents have only a high school education? So notice we have our independent variable, the two groups, with or without a college education. We have our dependent variable, the math SAT score. And we know what we are predicting or asking about is the score different, which indicates that this is going to be a two-tailed test. So now, let's take a look at these data in Excel. The data set that you will be working with for this example is this satmath.xlsx Excel file. Let's take a look at these numbers. We are going to do this test in JASP, so we have two problems right off the bat. Number one, JASP will not open an Excel spreadsheet in the Excel format, so we have to fix that. And number two, the data are not structured the way that they will need to be in order to do an independent samples t-test. So we need to fix both of those things. We're going to fix the second one first. Now, I'm going to begin by just adding a column in between these two. That will become apparent why I did that in just a moment. In order for us to do an independent samples t-test, we need to have two columns, one of which contains the data for our dependent variable, which will be a scale variable, in this case the numbers, and then we have a second column for the independent variable, which will be the groupings. Now, to create the groupings, all I'm going to do is just grab college, and I'm going to copy. I'm going to paste that, use some right-clicking here, paste it right there. Now, when I grab this, you see that little box in the lower right corner? If I grab that, I can just drag that down. It will copy college all the way down. So that means every score in column A comes from someone whose parents had a college education. How many were there? Well, our last line is 17. Our last row is 17. We can subtract 1 from that, from our header row, so we know there were 16 students in that category. Now we're going to copy and paste, or maybe we should just cut and paste the scores for high school. Again, cut, paste. And notice that instead of dragging down, I can also hover over that little green box and double click. That will copy the word high school for all of the remaining boxes. Now we need to clarify the variable names. So for where it says college, these are actually our scores. We'll call this our SAT math score column. And college and high school, we'll call that education. And just for fun, let's make that bold, although that's completely unnecessary because in the next step, all of that formatting is going to be eliminated. Now let's save this data set now that we have changed the structure of the data. And we need to fix our second problem, which is JASP does not open Excel spreadsheets. We therefore need to save as a CSV, comma delimited file. It will save to the desktop and go. I'm now going to just quit out of Excel. There's my data It's in it's in a CSV file. So now I'm ready to move over to JASP, and we can get to work with this independent samples t-test. I have now opened JASP. We can see that CSV file waiting for us there on the desktop. And the way that we will open that file is we'll go to the main menu icon. We'll select Open, Computer, and Desktop. You'll notice I'm not actually clicking on Open in Computer, just hovering over them. It opens up the next dialog box. Okay, I click on Desktop. We'll see that the SAT Math Excel file is not available, but the SATmath.csv is available. So we need to have a comma separated values file if we're going to open it in JASP. Click Open. And there's our scores. They have been properly recorded as scale level for the SAT math scores. And this is a string variable or a nominal text variable for education. Even though we're not using ones and zeros or ones and twos, even though we're not using numbers, we can still treat this variable as a factor. And we will in the next step. But first, we need to explore the overall setup for this test that we are going to do. And for that, we're going to go back to PowerPoint. Let's explore the 5 steps of hypothesis testing for an independent samples t-test. So step number 1, when we have data that we want to analyze, we need to figure out what kind of test can I use with these data. So step number 1, select the appropriate statistic. Well, this is always going to be the easiest step anytime that I'm teaching you about a new test, because the answer will always be whatever test we're learning right now. So this is simple. We're going to do an independent samples t-test. We're doing this because we have one scale variable, which is the math scores from the SAT, and one categorical variable with 2 levels, college versus high school. So one scale, one categorical. The categorical has only 2 groups. Next, state the null and alternative hypothesis. We are assuming that the groups will be different, but we haven't said whether they will be higher or lower than each other. Therefore, our null hypothesis is H sub 0 colon mu1 equals mu2. What does that mean? Mu is the mean of a population. So we are saying our first group, the college group, is drawn from a population which has a mean, mu, that is equal to the mean of the population from which the second group has been drawn. College is drawn from a population equal to the high school population, and here we're talking about population scores for the math SAT. All right, so where does that leave us? Our alternative hypothesis will therefore be mu1 does not equal mu2, because we are saying that these groups will be different. We're not saying one will be higher or one will be lower than the other, just that they will be different. Our null hypothesis is that the groups are the same. That's the hypothesis we will be testing. Our alternative hypothesis is simply that the groups will be different. Now later on, I'm going to show you what we do if we speculate that one will be higher or lower than the other. Step number 3, select a level of significance. To do this, we need to know a little bit about our setup. We're going to be doing a two-tailed test. We know that because we are simply saying the groups will be different, not that one will be higher or lower. If we said higher or lower, that would be a one-tailed test. Well, we're saying the groups will be different. That's a two-tailed test. Alpha of 0.05 is our standard alpha level. We can change that if we choose. Typically, we will leave that at a 0.05. Degrees of freedom is 26. Remember the group sizes. The group sizes were 16 and 12, collectively 28. The degrees of freedom are the n-1 for each group. So we could say the n1 group of 16 minus 1 plus the n2 group of 12 minus 1, total of 26. We will use this setup, two-tailed, 0.05, 26 degrees of freedom, to find a critical value. To do that, we can go to a table that is at the very end of your notes. It's labeled Students T-Distribution Table. Notice in this first set of columns, these are all for a two-tailed test. The very first column is the alpha 0.05 level. And we need to go down that column under degrees of freedom until we find a 26, and we find the value of 2.056. That is our critical value, a positive negative 2.056. Now, before we jump into the test, I want to show you one other tool that can be really helpful. It's called the effect size calculator for t-tests. This is something I developed several years back, and it's like a Swiss Army knife for t-tests. And I find myself going to this particular tool anytime I need to answer a question. I don't want to look it up in a table. I just need a quick, simple answer. Now, for this example, we want to look at the t-tests. So either click on the tab for critical values, or this is actually a link, which will get us there as well. And we're going to look at this blue box where it says critical t-value for alpha of 0.05 two-tailed tests. That's our typical setup. So here we see an alpha of 0.05. Here we see a two-tailed test. And we just enter the degrees of freedom, 26. We can click. We get that value of 2.056. Well, when can this be especially helpful? You may have noticed in the table for critical values that once we get to about 50, it just goes 40, 50, 60, 70. We don't have smaller gradations of degrees of freedom. Well, if we have 50 degrees of freedom, we have a critical value of 2.009, but if we have, let's say, 56, which is a value that is not in the t-table, we can get that critical value of 2.003. So this is useful for any degrees of freedom, and it's useful if we're doing, let's say, a one-tailed test. I can change this 2 to a 1. That changes my critical value. If my alpha level was 0.01, I could also change that and get the new critical value. But let's say that's a two-tailed test. New critical value. So this little device can be really helpful for finding those degrees of freedom if you don't want to look them up in a table. If you do, for whatever reason, want to look them up in a table, I've also included a t-table for a two-tailed test right here. So here we are back in JASP, and we are ready to do our independent samples t-test. Well, that is accomplished by going to t-tests, and under classical, we'll choose independent samples t-test. Notice that JASP gives us a hint as to what type of variables go in what box. So we're going to put our scale variable in the variables box. We see the scale. And we are going to put our nominal variable into the grouping variable box. Now from here, we're just going to use the same kinds of parameters as I've shown you in other examples from class. So for example, we will start with our assumptions checks. We will check for normality and equality of variances. And notice that the findings appear in our results panel as we go. Under additional statistics, let's get our location parameter. It's going to be our mean point estimator. And we will get a confidence interval of 95%, an effect size, coinc D by default. We'll get descriptive statistics and a descriptives plot. Now we can scroll around in the results pane. We can see all of the results, but to make this even easier, I'm going to click on this triangle in between the dividers, click, and now I'm seeing only the results. If I want to see the original view, I can go back to this. If I want to see the data, there they are. So I can move these panes around so I see only the things that I want to see. Now in the homework or on the test, there will be specific questions that you will need to answer. Let me give you an example of what those might include. What is the point estimate of the difference between the means of the two populations? Okay, that point estimate, that's a single estimator, a point estimate. That would be the mean difference. So our point estimator is going to be an 84. Compute the t-value, degrees of freedom, and p-value for the hypothesis test. So again, we look in JASP. The t-value is a 3.098. We can round that up to a 3.1. Degrees of freedom, 26. P-value, 0.005. So we're seeing it's very easy to get to these answers when we're using JASP. Our confidence intervals, our lower and upper confidence intervals. We see that they do not cross 0. And our Cohen's d effect size is a 1.2, which is huge. It's a big effect size. If you're asked about the assumptions checks, we would find those answers in this category. Now, for assumptions checks, so we prefer non-significant results, or results that are not less than 0.05 for all of our assumptions checks. And that's exactly what we see here. The p-value for the college group is a 0.46, which is not even close to 0.05. For high school, it's 0.2, again, not less than 0.05. Down here for our equality of variances test, it's a 0.3. None of these are less than 0.05, so none of these tests are significant. Now, that is what we want with our assumptions checks. It means that all of our assumptions check out. There are no violations of the assumptions. In our descriptives table, we see the group name, the sample size, the mean, standard deviation, and standard error for each of the groups, and there's our descriptive plots. Let me go back to the types of questions that you might encounter. What does the sample mean for the SAT math scores for each of the groups? All right, that you would find in the group descriptives box. So our sample mean for the students whose parents had a college education is a 552, and for high school, 468. The standard deviation is the amount of variability within those mean estimators, and the standard error of the mean is the standard deviation divided by the square root of the sample size. So for example, if we take 76.175 standard deviation divided by 16 square root, which is 4, we get that 19.04. Using a 0.05 level of significance, what is the p-value and what is your conclusion? I'm going to show you 3 ways to answer this question. So number 1, is our t-value greater than our critical value? So here I'm going to pull up that effect size calculator that I showed you. And for 26 degrees of freedom, 0.05 alpha level, two-tailed test, our critical value is 2.056. Well, 2.05 compared to 1. Well, 3.1 is greater than 2.5. That suggests that this test is statistically significant. Our p-value is less than 0.05. It is 0.005. You can think of this in terms of a dollar bill made up 100 cents. So a nickel would be 0.05 or 5 cents. This would be, well, much less than a nickel. And our 95% confidence interval does not cross 0. So what I mean is the lower bound is 28, the upper is 139. 0 does not fall in between those two. So if this boundary does not include 0, really what that means is if one is not negative and the other positive, all of these 3 converge upon the same conclusion, which is that our t-test is statistically significant. So let me put that in context of the 5 steps of hypothesis testing. When I say that the t-test is statistically significant, remember I'm testing this null hypothesis that says there is no difference. Well, that is the hypothesis that I now reject because I can see from the evidence that there is a difference, that in fact my alternative hypothesis is the best explanation. So I am rejecting the null. I am not accepting the alternative, but that is the hypothesis that I will say that there is evidence to support. That is based upon step 4. I have calculated these statistics. I have a t-value that is greater than my critical value. I have a p-value that is less than 0.05. And again, my confidence interval tells me the same thing. It does not cross 0. So the decision is that the groups are different. The college group, with its mean and standard deviation, was statistically significantly higher than the high school group with its mean and standard deviation. And now, because I know which group is higher, it's okay for me to say that this group is higher, even though my hypothesis was that they were different. And so now let me put all of that together in the APA style write-up. I'm not going to read all of this for you, but I'll point out each of the elements. So first, I'm saying, what is the result? The groups did differ statistically significantly. Always work in that phrase. I've written up the results of the t-test. The t-value with degrees of freedom, the p-value, the d, Cohen's d, is my effect size, and my confidence interval in brackets. And then I say what that means, and I want to include my means and standard deviations when I talk about each group. So students with a college whose parents had a college education, we see their mean and standard deviation, scored statistically significantly higher on the SAT math, our dependent variable, than the students whose parents did not have the college education or had a high school education. Again, their means and standard deviations. And then what does that all mean? Well, this supports the idea that parental education predicts academic achievement of the offspring. And let me clarify something about the choice of wording here. I've said that parental education predicts achievement among the offspring. Why did I say predict? Prediction is usually a phrase that we would use when we were talking about regression equations. Why did I use that for a t-test? Because in this case, we have not done an experiment. We did not have an experimental and control group that we randomly selected and randomly assigned. These are observational data. A researcher goes into probably a computer system somewhere, finds some SAT scores, finds some categories, college education versus not, observational data. So we can't say that the parent's education causes something about the student's outcome. We can say that it is predictive of. We're not going to use causal language when we just have observational data. Now this raises an interesting question. What if we were going to do a one-tailed test? What if we had set up our research saying that this business school admissions committee had hypothesized that student applicants whose parents had attained a higher level of education would, on average, score higher on the scholastic aptitude test? So we are predicting a direction of change, scoring higher, or in a different setting, scoring lower. How would we adjust the settings in JASP to answer that kind of question? Well, let me show you. So here we are back in JASP, and I want to be able to see the original settings. If I'm going to do a one-tailed test, the only change that I need to make, in addition to maybe enlarging this screen so we can see it a little better, is to change this alternative hypothesis. So by default, we're doing a two-tailed test where the first mean and the second mean are, in the alternative, not equal. What if we're saying that group 1, which is the college-educated group, would be higher? I just checked this radio button. Now, the test itself gets recalculated. Some things change, some things don't. So for instance, my t-value is going to stay the same. Degrees of freedom will be the same. My p-value will change. Mean difference and standard error of the difference will be the same. But my confidence interval will change from a lower to an upper of infinity because I'm only looking in that one direction. And the Cohen's d will not change, nor will any of the descriptive statistics. Well, what if I wanted to go the other direction? What if I wanted to predict that students of college-educated parents would score lower? Well, that would be group 1 is lower than group 2. And what you see here is that now the test has become non-significant because I am looking for change in one direction and I'm not finding it. So if I predict the direction of change incorrectly, then my test will be non-significant. It was significant in the correctly predicted direction or in the example where I'm using a two-tailed test. But if I wrongly predict the direction of change, my test will then become non-significant. Just an important thing to know about if you're going to use a one-tailed test. And those are the things you need to know about in order to do the test and the quiz for this week. So you know how to find the data in Excel, to structure that data so that you can use it in JASP. You know how to import that CSV into JASP, how to do the test, and how to interpret the test. So I hope that this was helpful in explaining the independent samples t-test.